So as you can see, quantum theory is essentially about multiplying and adding probability amplitudes and then taking mod squares and getting probabilities out of that. There is a very convenient mathematical tool that allows us to keep track of those probability amplitudes in a rather neat way. If you look at the example of quantum interference that we just discussed, you see that it has three different elements, which the first interaction, the first resonant cavity, the central cavity, and the second resonant cavity. Now, the probability amplitudes associated with transitions between input and output state can be nicely tabulated. So instead of drawing a diagram like this, I can simply write a matrix for you of probability amplitudes. So I tabulated them, and you can see that there is 1 over square root of 2 is the transition between the state ground and ground, and this transition between the state excited and excited is here, and this is a transition that the system that is in the excited state will be in the ground state, and this is a transition between the ground state and the excited state. And the same for the dispersive interaction. You can see that those off-diagonal elements here are zeros, but the diagonal elements correspond to the phase shifts of the ground state and the excited state. Now, instead of drawing different paths on this diagram and then multiplying probability amplitudes along each path and then adding probability amplitudes corresponding to different paths together, all I can do is just simply multiply the three matrices that correspond to different interactions in the system. So those the first one, the second one, and the third one. And if you do this multiplication, so this metric multiplication in one swoop, it takes care of multiplying and adding probability amplitudes corresponding to different paths. If you do the multiplication, you will get something like EI phi 1 plus phi 2 over 2, and then you will get a matrix which has cos phi over 2 on the diagonals and minus I sine phi over 2 on the off diagonals. So that means that this matrix here describes the effect of the concatenation of the three interactions in the system. Essentially, instead of writing and drawing this diagram, I can say that this diagram is equivalent to this diagram, where the transition amplitudes are cos phi over 2 and cos phi over 2. And the transitions between the ground and the excited state happens with probability amplitude minus sine phi over 2, and this is also minus I sine phi over 2. So that is the way we usually think about transition in physical systems. You simply just provide a matrix of transition amplitudes between the input states and the output states. If you look at this matrix here, again, we notice that the essential elements are those that depend on the difference in the phase setting. So that is by phi. Phi is equal to phi 2 minus phi 1. And there is a global phase factor in front of the matrix, but whenever we start taking probabilities, this one is equal to 1, so it's not relevant. So what really matters are the elements that depend on the difference in the phase setting. So all global phase factors will be then ignored later on in this course. I would then like you to understand this interference again as a sort of sequence of three operations on, in this case, on the energy levels of two selected energy levels of an atom, and try to think about those 3 boxes. That kind of diagram, it's instructive for pedagogical purposes. I can draw it and easily explain how it relates to transition amplitudes and matrices that we construct. But it is not very convenient to draw that kind of diagrams when we analyze a physical system undergoing quantum interference. It's much more convenient to draw a diagram like this, where this horizontal line here represents a quantum system that undergoes 3 different consecutive interactions here. So on the left we have the first operation, and then you will see later on we'll call it the Hadamard gate. It's elementary operations in quantum information science, one of the most common, the most important one. In this case, again, it just opens 2 different paths for quantum interference to happen. Then we have a phase operation, then we will call it the phase gate later. And that is actually, it looks innocuous, right? That little dot with phi on it, but it's actually quite important. What it does, it controls the output. This phase gate here, sandwiched between those 2 Hadamard gates, is actually quite essential. So we see that we open quantum interference with the Hadamard gate, we control quantum interference with the phase gate, we close the path, and therefore just make quantum interference happen in the system with a second Hadamard. So this sequence, Hadamard, phase, Hadamard, is a sequence that we are going to see over and over again, and it will be actually the most important diagram that you will see many times, and it's actually therefore very important that you understand every single element in this diagram and what it does.